Have you ever just stopped and wondered what controls the speed of, well, pretty much everything? I mean, from the way your body processes medicine to how food cooks on the stove, there's this hidden clock ticking away behind the scenes. Today, we're going to peek behind that curtain. We are diving deep into the science of reaction kinetics to figure out the hidden speed of everything.
Seriously, think about it. Why can't you just pop one painkiller and be good for the whole week? And what's the actual magic behind a refrigerator that keeps your food from going bad? Well, turns out these aren't just random quirks of life. They are both governed by the exact same fundamental principle, the speed of chemical reactions.
And right here, this is our first big clue. This number, 2.5 hours, is the entire reason you have to take another paracetamol pill every 4 to 6 hours. See, after just 2.5 hours, half of the active drug in your system is already gone. It's been broken down by your body's own chemistry. This is what we call the drug's half-life.
Okay, so let's dig into that idea of an internal countdown timer. Because if you can wrap your head around this, you'll understand exactly why that painkiller's effect starts to fade. So, what is a half-life officially? It's really simple. It is just the amount of time it takes for half of a substance to get used up, to decay, or to be consumed in a reaction. It's the ultimate measure of how fast something disappears. But here's the catch. Not all countdowns work the same way. For things like drug metabolism, which we call a first-order reaction, the half-life is constant. It doesn't matter if you take a big dose or small dose, half of it will be gone in the same amount of time. Now, for other reactions, zero-order ones, the countdown speed actually changes depending on how much stuff you start with. But for now, let's just focus on that steady, predictable decay. Radioactive decay is the absolute perfect example of this constant countdown. So, say we start with 1 gram of some element, and it has a 140-day half-life. You can see the pattern plain as day. After 140 days, boom, half a gram is left. Wait another 140 days, and it halves again, down to a 1/4 gram. It's this predictable, relentless decay just having itself over and over again, right on schedule. So we get it. Reactions have a speed, a half-life. But why? What is it that actually sets the pace? Well, the answer is all about energy. Let's meet the energy gatekeeper that's in charge of every single chemical reaction. Every reaction in the universe has to overcome an energy hurdle. Seriously, think of it like a high jump at a track meet. The molecules can bump into each other all day long, but unless they collide with enough force, enough energy to clear that bar, the activation energy, nothing happens. They just bounce off each other, and that's it, no reaction. So how do we help these molecules clear that hurdle? Simple. We add heat. The warmth on your kitchen counter gives those spoilage reactions more energy, so they happen way faster. In fact, there's a pretty handy rule of thumb in chemistry. For a lot of reactions, just a 10 degrees Celsius rise in temperature can actually double the reaction speed. That's the power of putting something on the stove. Or in the fridge. Now, all of this is wrapped up neatly in something called the Arrhenius equation. Don't let the name scare you, and you definitely don't need to worry about the math. The big idea is this. A reaction speed is basically a constant tug of war. On one side, you've got temperature and how often the molecules are colliding, trying to speed things up. But on the other side, you have that massive energy hurdle, the activation energy, trying to slow everything down. Whoever wins that fight determines how fast the reaction goes. Just like the scientist Arrhenius himself said, it all comes down to the height of that energy barrier. If the barrier is high, you get a slow reaction. If it's low, you get a fast one. And that simple fact, that's what gives us the power to take control. And because we know this, we can become the masters of speed. It's like we have this toolkit with 5 different levers we can pull to intentionally speed up or slow down pretty much any reaction we want. And here they are. These are our 5 levers. We can change the very nature of the substance itself, how concentrated it is, its surface area, the temperature, and this one's the real game changer, we can add a catalyst. Let's start with the state of the reactant. If you just mix 2 solid powders together, the reaction is painfully slow. Why? Because only the molecules on the very surface can touch each other. But what happens if you dissolve those same solids in water? Well, now the molecules are free, zipping around, ready to collide, and the reaction happens instantly, in the blink of an eye. Surface area is another incredibly powerful lever. Take a solid chunk of marble and drop it in acid, and yeah, it'll react, but slowly. Now grind that same piece of marble into a fine powder. You've just massively increased the available surface area.
Suddenly, way more molecules are exposed, way more collisions can happen at once, and that reaction just fizzes away like crazy.
All right, now for that secret weapon I mentioned, the catalyst. A catalyst is like a chemical shortcut. It doesn't actually get used up in the reaction itself. Instead, it brilliantly creates an easier, alternate route for the reaction to take, a pathway with a much lower energy hurdle. I mean, just look at the difference here. Without a catalyst, the reaction has to climb this huge energy mountain to get to the other side. But when you add a catalyst, it's like building a tunnel straight through the mountain. The peak is so much lower, which means way more molecules have enough energy to make the journey, dramatically speeding the whole thing up. So what's the big takeaway here? What does all this mean for us and our lives? This isn't just some abstract science for a textbook. Understanding and controlling the speed of reactions is, frankly, at the very heart of our modern world. Think about it. We use kinetics literally every single day. The medicine we take is designed specifically around its half-life. The food in our fridge stays fresh because we're using cold to slow down those spoilage reactions. The materials, the fuels, the plastics we rely on, they're all made efficiently because we use catalysts. Even cooking dinner is just applied kinetics. We're using heat to speed up all the tasty chemical reactions that turn raw food into an amazing meal. So we've learned to pull the levers and manipulate the hidden speed of the world around us. And that leaves us with a really exciting question. What's next? As our control over these fundamental speeds gets even more precise, what problems that seemed impossible today could we finally solve? What incredible new technologies could we create? That, right there, is the amazing frontier of reaction kinetics.